Integration of the power electronic modules into the electric motor housing, it is possible to obtain a more compact, high-power dense electric motor drive. Moreover, this structure allows to have a more fault-tolerant operation. In this video, I will present you the key aspects of an integrated modular motor drive. So what we've done, we've taken an axial flux motor design, and we have integrated a full power electronics platform around this motor, being thermally and mechanically coupled directly onto the electric motor. In our axial flux design, we originally had 15 stator coils, which in this design are each connected to a power module. Such a power module consists of a half-bridge topology, in this machine implemented into 650 volts silicon carbide technology. These modules are operated at 400 volts at a switching frequency of 100 kilohertz. So what we see is that each of the motor coils is driven by one power unit. And you can also see that in this case, the cooling system has also been made modular. This is more for research purposes rather than this would be the case in industrial application. What else do we need? So we have a motor, we have power electronic modules to power them. Well, of course, they have to be supplied by a certain DC voltage. So therefore, we created an actual additional PCB with some bus bar rings below. So each of the bus bars contain, well, the first two contain the DC minus and the DC plus voltage. And then we have some bus bars that are used to make the start point. So in an external way, also for flexibility and research purposes, so at the outside of the machine. And on top of these bus bars, there is a current sensor board, which exists of 15 current measurements, of which in this case only 3 are populated. On the other side, we have our digital I/O board. In this prototype, of course, we have our controllers outside the machine. This means that we still have cables connected to the rapid prototyping platform. But in a real application, this is, of course, the place where we will put the different microcontrollers driving the motor. We also, and it's less visible, but we also implemented on this side a low-resolution position sensor. This is a cheap alternative to the high-cost electric encoders that offer both the advantages of having a real rotor position measurements, as well as the ability to derive a high-resolution position sensor from these sensor data. It's an integrated motor drive, so I said we are going to save space, so volume and mass by assembling everything together. And you can clearly see on the other side of the motor, where I have removed some of these modules, that you can see the real housing of the motor. As you can see, it has we have introduced flat surfaces in such a way that we can mount our silicon carbide FETs directly on this part to have, of course, the cooling capability to cool down the module. So this is more or less the concept. So this device acts both as a housing, so the mechanical housing, as it serves as a cooling interface, so actually a cold plate for the power electronics. So this is basically the design. So as I told, it switches at 100 kilohertz. So this makes the stresses on the capacitors much less. Therefore, this is implemented using only ceramic capacitors. You can see the array clearly on each of the power modules. So I hope you understand already why we have a more compact, high power density drive, but I also told that there is some room for fault tolerant control. And I will, in the second part, I will explain why and how we are going to achieve this. So as you can see, we have 15 stator coils, we have 15 modules. So what have we done? We have split up these 15 modules into 5 groups of 3 modules. Each of these 3 modules, they just act as an ordinary 3-phase system. So this means that or what have we done? We have chosen each time 3 of these modules. We connect them onto a standard controller with, of course, the low resolution position sensor input, and of course also the current measurements on the other sides. And for fault tolerant purposes, we connect them into a different start point than, of course, the other 5 groups. In such a way, we have obtained an inherent multi-agent system. And a multi-agent system, well, there are, of course, the different ages, which are in our case, the 3-phase system, they can work together. So instead of having a master, we just give some kind of set point to the group. We say, for instance, we want 15 Newton meters torque, and then these modules will decide among themselves how they're going to spread the power or the torque among the different agents. So this is how it works. If, for instance, one agent gets too hot or has another failure mode, then it will just detach from the system, and of course, then the drive can still operate with the 4 remaining agents. So this is how it works. So we have this redundancy in our power modules, in our motor modules, in our current measurements, in our microcontrollers, and also in our position algorithm. So this means that by doing so then I mean the real modular and integrated motor drive, we can obtain a high power dense, compact, and fault tolerant drive. So this is basically the message that I wanted to give you today about this prototype. Perhaps for your understanding, you've seen already my hands, so this is more or less the scale of the machine. So the machine is about, so this dimension is about 25 centimeters, and the machine should be capable to handle a continuous power of 15 kilowatts. The mass is about 9 kilograms, so you can do some calculation yourself to get an idea about the power density of this drive. But I have to admit it's more a proof of concept rather than an optimization in terms of power density. So there is still some work for us to do in the coming years. Thanks for watching.